All right. Morning, everyone. Hello, people online. We have a packed room here. I'm Leandro Coelho, for the ones that don't know me, and I'm organizing this seminar alongside Marilene Scherkesli, who is online, and in Montreal. So we are here in Quebec City. This is a seminar organized by the GERAD, who graciously support my colleague Walton with a postdoctoral fellowship co-supervised by myself and Marilene, hence the organization of the seminar. Welcome, everybody. It's my pleasure to be here with you and to introduce Walton, who is doing then this postdoctoral fellowship with us. He is based, hello, John, who is, so Walton is based here in Quebec with us now for logistics reasons. And we're working together with Marilene, and today Walton is going to present to you a part of the development that he has been doing with us for the past 9 months. 9 months already. Time flies when you're having fun. So Walton got his PhD from in OR from the University of Southampton in the UK a couple of years ago, and he has since become assistant professor at the University of Universidade Federal de Pernambuco, in Pernambuco, where he teaches in the industrial engineering program with lots of optimization, as we do and as we like. And so Walton, during his postdoctoral fellowship with us, he's introducing us to the field of optimal control, and we are trying to merge that with the field of optimization in transportation. And this is what he's going to present to us today, his work on optimal control-based approach for the Dubins Travelling Salesman Problem with the Neighbourhoods. So Walton, thanks a lot for being with us, for accepting to give this seminar today, and the floor is yours. It's going to be a typical seminar organization. Let him talk for a good 45 minutes. In the end, we have a good 15 minutes for Q&A for interactions with the presenter. All right? Thanks a lot. Enjoy.
So, first of all, I'd like to thank everybody who is here, present and also online, for to see the opportunity I have to share my work. So, yes, that's So I'll talk a bit about unmanned aerial vehicles, which are drones. Talk about Dubins vehicle. I think I have to introduce it for you. Talk about my problem and how we are attempting to solve it. Okay, so drones, they are almost everywhere nowadays. We have several types of drones, and for every type of operation, we have drones that fly from 7 minutes to 34 hours with a range of 25 to 33,000 kilometers. Speeds vary a lot, payloads vary a lot as well. Sizes vary a lot. You can have a drone that fits on the tip of your finger. You can have a drone that's the size of a truck, basically. And the costs also vary basically on the type of technology. Also, the types, they vary a lot. So we have the famous predators, which are very popular. You have hybrid drones. You have drones made of paper. Those ones are made in Southampton. They are gliders. They don't have engines, but they are controllable somehow. 3D printed drones. So they all vary in the type of operation, in the type of missions that they can accomplish. So drones, you can have, basically for any vehicle, you can have two types, which are the manned vehicles. Manned vehicles are the ones that need a pilot, a driver, or something. So they must be operated by a pilot. Some are computer assisted, like airplanes. But in general, the driver or pilot is in control, at least you hope, not like in the movie. Unmanned systems, they are a bit different because they don't have a pilot. Here, I'm going to focus on autonomous systems or robots. So robots, they don't have a pilot or driver involved. In most cases, you have to provide detailed and specific instructions how your vehicle is going to move. So you have to give it reference trajectory and reference controls, so that the onboard computer, like this one, knows what to do. So you have to say, you have to turn right, left, you have to move these flaps, you have to do a roll or something. You have to tell everything. And in the case of drones, flight dynamics needs to be considered. So we have to consider Newton laws, winds, and so on. So this is an example of onboard flight control system, which is basically the UAV's brain that you have to teach how to fly. So we go to the Dubins vehicle. The Dubins vehicle, so this started with Markov. He posed the problem: what is the shortest planar path with bounded curvature connecting 2 points? So you're giving 2 points, you're giving 2 tangent angles. You have to find a bound curvature path connecting those 2 points. And Dubins in 1957, he proved that between 2 configurations, in a configuration is a set of 2 positions and 2 tangent angles, you have only 6 possible paths, and one of them is the path of minimum curvature. So you have to have 2 points and 2 tangent angles. So nowadays, the Dubins vehicle is a subject, very popular subject in optimal control. Modern approaches, they use optimal control to deal with Dubins vehicles, and it's modeled like that. So this is the model for the Dubins vehicle. So it's a set of 3 differential equations that govern the movement of the vehicle. They basically describe how to move in the X and Y direction. Those are the first 2 equations. And the third one is the orientation. So here is our paper drone, so to say. Since Douglas inaugurated the era of sound effects, I have to do one. So if your drone is struggling like that, this angle here gives you the heading orientation, so where it's pointing to. And the variable u, you see there, u of t is a function actually. It gives you how to steer, so right or left. Okay, so those 3 sets of equations there, they model the movement of the Dubins vehicle. And the Dubins vehicle is a widely accepted model to model the movement of drones in the literature. So because it's somehow simple model, it's somehow tractable, and it is very good for modeling the flight of fixed wing drones, so like mini airplanes. And it has some other varying applications everywhere. So it started with a railroad design by Markov in 1889. Nowadays, it's very popular for modeling drones. Also, you can adapt this model to consider, for example, battery consumption, wind conditions, so any kind of complicating aspects. Maritime vehicles, ground robots, well-bore trajectories, which are trajectories for perforating the rock and extracting oil, and also underground mines. Okay, so now we go to our problem. Which problem we are studying? So this problem, the Dubins DTSP with neighborhoods, was proposed by Obermeyer in 2009. It's a conference paper, and in 2012, the journal paper, so to say. It models a situation where a fixed-wing aircraft performs reconnaissance missions using electro-optical cameras. So the problem is you have a target you want to photograph, so to say, it's in an urban environment or so, whatever. The camera has a range, which is given by this. And then if you consider that your drone flies, is in a coplanar flight, so it's not changing altitude, which is a reasonable assumption, consider the size of the drone and the size of the world. You can model the field of view of the cameras as a continuous neighborhood like that one. So it has some assumptions. The flight dynamics is approximated by a Dubins vehicle, planar flight, and free airspace and no wind. So what we have in the literature up to now, basically all the papers dealing with this problem are heuristics. Obviously, it's a very difficult problem. So we also have some approximation algorithms with approximation factors of 1.9 roughly, but also under very restrictive assumptions. They have to assume a very strong, actually, assumptions. And most of the papers in the literature, they deal with the trajectory optimization as a black box. So I'll go back a little bit. So if you notice, I highlighted here path in the Markov problem. And I highlighted here trajectory when I define the equations. And the difference is basically, you go home, you go to work, you leave your house, you go to work, you can get a map and trace your path. But the trajectory is different. You have to know, you have to have a timestamp in your path. You have to know how to, if you go right, if you go straight, if you go left, and so on, how to steer your car. So this is a trajectory, basically. The description, a time description of the steps you take to achieve your goal, okay? So let me go. So all the papers, the path planning, most of the papers, sorry, they deal with the trajectory later. So in our problem, let's skip this. I'll go to the picture because it's better. You have a starting position for your drone. You have targets. You have to visit. And you might possibly have also visiting angles, which are given by the dashed lines. So you need to find a trajectory for your drone, visiting all the what we call neighborhoods, which are continuous regions. You have to minimize some performance measure, and your variables are the control function and the state trajectory of your drone. Okay, so you have to minimize a functional like this one, and you have to find the trajectory which is given by the state, the controls, and also the flight time, which we might want to minimize. Okay, so the problem is very easy to describe. So what are the main contributions of our work? It's the first exact approach with finite conversions for this problem. So it's also the first exact approach that works on the control and state space in a simultaneous manner. And the first exact algorithm that does not rely on the discretization of the neighborhoods. Okay, so first approach to solving is what we call single phase formulation. In our single phase formulation, we have as parameters a set of CI neighborhoods, continuous neighborhoods, and the vehicle parameters, which are they define the equations of motion that I showed you before. And our decision variables are the functions x, y, and u. So function x, y as the state function in the x position, y position, and the control function. I forgot to put here, but also the final time is a decision variable. And this is the formulation. Okay, so we minimize a cost functional, which for simplicity we define as the flight time. This I put an integral here just to emphasize that this is a function actually. It's not a function, it's a functional. But if you integrate, it's just the final time. You have the dynamics, which is the set of differential equations you use to model the Dubins vehicle. We have event constraints, so basically fixing the starting position and the ending position. We have path visiting constraints, which are the constraints that make you go there and visit the targets, and the domain of the variables. So this is a very standard optimal control formulation for any optimal control problems. But this actually the first time this has been done for this problem. Okay, so I'll let you keep this formulation here in mind, and then I'm going to how we attempt to solve this problem. So we consider a complete graph G, so we are all used to that. The only difference with this graph is that the set of vertices is the set of continuous regions you have to visit, the set of targets. But the set of edges, they are actually functionals connecting the regions. Each functional is a mapping from the domain of this strip, this tuple here to the real space, and computes the cost of traversing the edge I to j. So the graph G actually is not a standard TSP graph as we are used because we don't know the arc costs. So I'll give you an example here. So let's suppose we have this graph 0, 1, 2, and there's something in the middle, and then there's the other side of the graph, whatever. We don't know the cost from going from 0 to 2, because the cost from going to 0 to 2 depends on the whole trajectory. So we have to know the trajectory to know how much the costs, how much it costs to travel from vertex to vertex. So we get this situation that you need to have the route to compute the trajectory, but you have to know the trajectory to compute the cost of the route. So what do you do? So the graph is defined like that. We have the functions that compute the costs. The only thing that you have fixed in the graph is the starting position and the starting time. Everything else is dependent. So here we have to have constraints that make sure that this connects to this if we fly this way. So you have to compute the final time, the initial time in this arc here is equal to the final time of this arc if we travel this arc, these two arcs consecutively, and so on. So you have to do that. And then we go to actually, there's no assumption here. We can show that the visiting constraints can be defined only for the final time in each vertex. There's a property for that. And then we define the usual binary variables, that's one if we travel that arc or not. Then we can model our problem as a mixed integer optimal control problem. So in this problem, the object function, you have to minimize the total flight time as before. You have the usual assignment constraints. You have the dynamics, but now you only use the dynamics if you use that arc. So we have to multiply by the binary variable here, which is going to turn on and off. And then the event constraints, they look very ugly. They do not look like the ones we had before, because we have to have all those nasty binary and continuous multiplications over there to turn on and off the arcs that we are going to use. And then you have your path constraint here, which is defined like that. I'll just go back a little bit here. So what's the difficulty of those path constraints is that you say that for some time, at some time, you have to visit neighborhood Ci, but you don't know which one is it. So you have the whole domain of time, and then you have to choose one and connect and then plug into this equation here and see if you visit or not. For this one, even though we can fix a visiting time fix because we don't know it yet, but it's only one. You have to multiply by xij because you don't know if you're traversing that arc or not. But if you know, then you go back to the not to the single phase formulation, but you go back to a normal trajectory optimization problem where you have trajectory, you have to solve it, and that's it. So this formulation is pretty intractable. We do not solve it, but it gives us an opportunity to devise an algorithm based on decomposition. Because once I know, if I know the sequence, I go back to a multi-phase trajectory optimization problem, which is not easy to solve, but is solvable. So we go to a Bender's decomposition, a generalized Bender's decomposition algorithm, which is actually simple. We have an initialization with lower bound to upper bound. You check optimality. If it's not optimal, you solve the master problem. If the solution is integer feasible, so you have a root, you have fixed the root, you can compute a trajectory associated with that root. If you compute the trajectory and you find the trajectory, you can add an optimality cut to your master problem. And then you go again. Oh, if your solution is not integer feasible, then we do TSP stuff, compute subtours, outcuts, and add to your master problem, and then everything again. So I start with the initialization. I'm going to talk about this, and that one. So initialization, we start computing a lower bound on the flight time between two neighborhoods. So a very trivial one is the Euclidean distance between two neighborhoods. The disadvantage here is that if your neighborhoods, they overlap, your Euclidean distance is 0. So you get no lower bound, no useful lower bound. We devised this problem to compute a slightly better lower bounds, which is computing the Dubins distance between two neighborhoods using optimal control. So you define a problem where your starting point here is free, your end point there is free. You want to minimize the time. And the advantage is that even if the neighbors, they overlap, you might get a non-zero lower bound. And for this, we solve this problem here. So here, the event constraints, they are not fixed like in the previous formulation, they are free. But then using this formulation, for every pair of neighborhoods, we solve this problem and you compute the bounds. So lower bounding computation gone, we go to the master problem. The master problem is TSP formulation. So we have a graph, we have the set of arcs that connect vertices. And we have two sets here that I want to emphasize. S is the set of feasible roots of size n, so integer feasible roots, actually. And R is some set of infeasible roots. Cij min is the minimum, is the lower bound we just computed using the previous procedure, and decision variables as defined before. So this is the master problem. So probability cuts, you can understand as a sub-2 elimination cuts here. And the optimality cuts, we are going to compute the value of delta R for a given root. That's the optimal travel time of that route. And then you use delta to, oh, it's working now. Very good. To update the lower bound in the objective function. So TSP formulation, very, very easy. So how do we compute this guy here? How do we compute this guy here? This guy is given by the solution of this optimal control problem. So this is a multi-phase optimal control problem. By multi-phase, go to the definition of the graph for the original problem, which is we have to connect arcs in the root. Okay, I'm going to go. The only thing you have to make sure, which is different from the previous formulations, is that you have to connect the states, controls, and the time between different arcs. So yes, so this is defined as a multi-phase optimal control problem, which is still a challenging problem to solve, but it's solvable. And by multi-phase, I mean, By multi-phase, I mean that the trajectory is actually split between arcs. So you have a phase or arc one. Phase is how they call it in the optimal controls, but it's just an arc. You have three boundary conditions, so you don't know where to start in the first arc, but you don't know where to finish. So you have to compute it in your optimization problem. You have the set of differential equations for this arc, and then you just need to make sure that this guy here connects to this guy here using linking constraints. And then you go on. But this is all solved simultaneously. It's not like solving one and then the other one, and the other one, then the other. You have to solve everything all together. Okay, so how do we solve those trajectory optimization problems? We use a technique called direct transcription method for optimal control. And this works by, so first, we define time, we discretize the time. So we define a time set of size big N. So you get your time, your continuous time interval, you discretize it, and this is the equation that computes the discretization. So you use a time step eta, which is this value here. And then we assume a uniform time grid, just for simplicity. Then you say that you discretize state and control variables. They are approximated. So those are the variables. They are approximated by YT and EUT using forward finite differences. So you assume that you assume that this approximation is good enough at the time discretization points. And this is the error of your discretization. So this is the error where this function here is whatever method used to integrate the dynamic equations, the differential equations that you're using to model the Dubins vehicle. So in our work, we propose to use the Runge-Kutta family of integration methods. This family of integration methods, it works more or less like this. So the blue line is the real trajectory, so to say, so the exact trajectory. And then you use samples. The classical Runge-Kutta method use 4 samples. That's what you see there with K1, K2, K3, and K4, which are linear approximations between the 2 time steps. And then you kind of average those linear approximations to get an approximation of the real trajectory. And the equations look like that. So this is you get this part here. It's exactly here, and you have your time step here. So this family of methods is defined by parameters beta, alpha, and rho, in which rho is defines an interpolation of your control function. So you can use, for example, piecewise constant interpolation, like you use a linear interpolation or whatever interpolation you want to use. But the method is completely described by those 3 parameters here that you can put in a table like that. So this table here is called a Butcher tableau. And by the values you put here in your table, you define different integration methods. So if you recall your numerical mathematics class, you could use like Euler method, trapezoidal method, and so on. So for example, the 4th order Runge-Kutta method is defined by this table here. So that's the table of the parameters that you should use here to have your approximation of the real trajectory. Yeah, so that's it. We define those equations here. Those are the discretized differential equations that you are going to put in our optimization problem now and try to solve. The difference that now we have real variables. They are not functions, they are variables defined in the real space, which are those guys here. There's one thing else I want to comment, which is the error, in your approximation, this guy here. So the Runge-Kutta method is said to be a 4th order error method, because the error in the approximation is the size of the time step to the power of 4. So the power of the size step is the error that you are going to have by approximating this. So different values that you put here give you different approximation errors. So for example, Euler is 2nd order, so it's eta to the power of 2. That's your error, discretization error, so on. Okay, so we go to numerical experiments. So we generate some instances because we couldn't find any instances in the literature. We consider n compact sets with n-1 regions of interest and 1 starting point, which would be the depot. The location of the neighborhoods, they are in a square of 16 by 10. Each neighborhood has could have actually an assigned visiting angle. And the shape of the neighborhoods that we consider are circles, just for simplicity. And then we generated instances 8 to 30 vertices in a total of 260 instances. Just drink a little bit of water. Okay, so we coded the algorithm in Python using Gurobi to solve the master problem, the NLP problems that we have implemented also with Python using Pyomo. And the solvers, we use IP-opt to solving the subproblems in our Bender decomposition algorithm. And the single phase formulation that I presented you before, that I asked you to keep in mind, was we tried to solve it using Nitro. However, Nitro, we tested several solvers actually. Nitro was the only one to manage to generate some sort of solutions. But it's running on its heuristic mode because the problem is non-convex, so it cannot prove, sometimes it cannot prove convergence. And we have two computing environments. A small computer is the one in my desk, and in our cluster. So as I told you before, we tried several nonlinear mobile optimization solvers, but Nitro was the one that managed to find some sort of solutions. We did some computational tests for tuning the algorithm, so number of threads. We are running only one thread because it doesn't matter if you use 4, 8, or whatever threads. We tested several solvers also for the solution of the subproblems, but we chose IP-opt, which had the best results. And we also test many different integration methods here. Keeping in mind that each integration method actually define a different formulation. So at the end we test the 5 but 6 because trapezoidal tried 2 versions. So for the computational tests, testing the different integration methods, I'm in the table here ignoring the ones that were not good. Only kept the 3 best ones. But actually, the only thing I want to highlight from this table is that one thing, we don't have a clear winner here regarding the objective functions. The other thing is the time. The problem, we managed to solve instances with 6, 8, and 10 with reasonable gaps. Then the performance completely deteriorates. So 6, 8, and 10. So just to make sure, the version here we're trying to solve is the version where the neighbors do not have a required visiting angle. So this is free for the optimizer to choose. Okay, so we can solve up to 10 neighborhood points. Is that good? Let's see. So those are some computing time statistics. I forgot I put this table here. The thing I want to emphasize is the time we spend doing trajectory optimization is 99% of the total running time of the algorithm. So the whole integer part, the whole Robbie part is 0.01% of the time. I'm breaking up this time here into the time we spend with NLP solving, which is 60, for example, 64% of this total time here. And the other part is heuristics initial guesses. But as the problem grows, the time we spend with heuristic initial guesses gets more insignificant. These instances are very small, actually, so the initial guess is almost the exact solution. Okay, but is that good? Now we compare our solutions against Nitro's. Long story short, Nitro cannot solve most of the problems. You get feasible solutions, yes, with very bad costs, but they cannot prove optimality, so most are heuristic solutions. We get 2 solutions here with gap 0, but those are the costs against the cost of our algorithm. Computing times are also we also are much better by far. So those are instances with 6 vertices. Instances. Oh, it's something I want to show. I was curious about those solutions here that I'm highlighting in blue. They are very close to our solutions. So I want to investigate how they do that, but they do that by cheating. You see there's kinks here. So the solution is integer feasible, but it's not feasible for our problem. I don't know why. Solver is a little bit of a black box, so I don't know what's happening basically. But yes, you can see that our solutions are feasible. So this instance, this other instance here. Oh, something I also want to highlight. This is a computational thing actually. Because we are using IP-opt to solve our trajectory optimization subproblems, the solution is still local optima. So that's why you can see those loops here that look unnecessary. But actually, there's no way around of that. That's something that you have to live with, basically. They're not very common, actually. Same thing for 8 vertices, basically same results. And then I compare again 2 types of solutions. And here as well. Okay, so now we go to a variant of the problem we study, which is the one with prescribed angles. So this is justified. So having a visiting angle in each neighborhood is justified by the type of application you're considering. So if you're considering that your drone is trying to communicate using sensors with your neighborhood, this communication can use, for example, isotropic data transmission, which is communications the same in all directions. But if you're using something like a beamforming, like your communication goes in one direction, you're using a powerful 3-4 powerful antennas to communicate in a direction. You have to actually point your antenna to your target in order to communicate. So you have to have some angle to visit. So this is just some random graph of beamforming. In this version, I'm not comparing against Nitro because out of the 260 instances, Nitro only found feasible solutions for 5 instances. So I'm going straight to my algorithm. And here we see some better computational performance. Now we can solve with reasonable gaps, instances up to 20 vertices. Computing times, they are, let's say, reasonable for this kind of problems, but also the nonlinear optimization is still more than 97% of the time we spend. So yes, with this version, we can solve bigger problems because we are basically eliminating one state of the aerodynamical system. It's fixed. Here, some solutions. I'm comparing here solutions without prescribed angles in this side and with prescribed angles in that side. So you can see that the rules, they actually change considerably because the trajectory has to do all the bending and all the steering stuff in order to meet the requirements on the angles. Also, the control functions, they change a lot. For another example, here instead of just going straight from 3860, you have to do all those bending and deviations and everything. Okay, conclusions. So we propose an optimal control for the Dubins TSP with neighborhoods. we formulated as an integer optimal control problem. We attempt to solve using a Binder's decomposition algorithm. We can solve relatively large instances. 13, I don't know, 20 points is huge for this kind of problem. And the framework is flexible. We can handle some DTSPN variants. It's something that I actually didn't comment very well, but you just need to change the dynamical equations in order to model different kinds of vehicles and problems. So it's very flexible, actually. You can just, I cannot say anything about the performance. Some references, and I would like to thank the University Laval, GERAD, and Health in my university for supporting this research, and thank you very much.